Okay, question 21. Question 21, you are asked to deduce the latent heat of vaporization from the graph. So in the graph, they didn't tell you which part of the graph is undergoing boiling, because when you want to find out latent heat of vaporization, you are talking about boiling. But they tell you that the substance start at a solid state. So it will be solid, 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 melting, liquid, 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 boiling, then vapor. So meaning that at this point of time, it is going through a state of change and it is boiling. So you know that here we are talking about boiling, and it actually boiled for 2 minutes. So we need to find out how much energy is involved here, and you were told that the heater is 1005 W. So with this, just be very careful. This is 2 minutes, change it to seconds, and you'll be able to find the total energy involved. So once you have that, put it into your latent heat formula. So Q equals to mLV. Plug in all the things. You were told the mass is 2 kg, so you can find out what's your LV. Question 22. This one is quite simple. Assume no energy lost to the surrounding, and you are asked to find out what is the mass of the water, the liquid water. So I will just zoom in to here, and okay, it autofocus. Okay, so the energy loss from the water must be equals to the energy gained by the ice. So energy gained by the ice has two parts. One part will be used to change the state. That's why you just use mass times latent heat of fusion, plus to raise its temperature from 0 to 45.5. So this whole thing will give you the energy gained by the ice. And down here, the water doesn't go through any change of state. It's only going through a drop in temperature. So just go and just find out with your specific heat capacity how much energy is lost this way. You already know the mass of the ice, so you only have one unknown, which is your mass of water. So here, do your algebra correctly, you will get your answer. Okay. Question 33. Question 33 is quite interesting. What you need to be careful is that the maximum, how do he put it? The maximum length that he can see will means that the light is going to bounce at the edge of the mirror. So it is about geometry again. So what I did is I just sketch it out. So what happened is that from floor to the ice is 1.2, and so the height of the mirror is 1, meaning that you have 0.2 here. So if you have 0.2 here, then the triangle, the biggest triangle that you can find is just 0.2 here, and then another 0.2 here. Okay, to have this triangle. So you know that your eyes can only see up to 0.4 meter from the eye level. So quite simple, but quite intimidating, I have to admit. When I first look at this question, I'm like, oh my god, what to do? Then I tell myself, okay, let's try sketching it out. Then everything works out fine. So moral of the story again is, don't give up, just try out different approaches. Okay? Once you give up, it's going to be 0. If you approach it, you learn something from it. Okay, this one, you need to be very careful about the definition of angles of reflection. Okay? The angle of reflection is always measured from the ray to the normal. Okay? And the sketch here is not to scale, so don't be fooled by it. So you started off with the angle of incidence of 60 degrees, so it's going to reflect, so you are going to have 60 degrees here. Meaning that the angle here is going to be 30, because it makes a right angle, right? So 90 minus 60, you got 30. So you will have this triangle to consider. So I know it looks really weird, but just imagine that, okay, now you are focusing on y, okay, and you know that you know that you have an angle here 60. Then you were told that, okay, now there's a ray coming in. You do not know how the ray look like. You just know that, okay, there's a ray coming in, and this is 30 degree. Okay, you just know, you just find out, you just focus on this part. So just looking at this triangle, you know that, oh, okay, here's 90. But is 90 the angle of incidence? No, right? Because this angle is between the ray and the mirror surface, the boundary. And that is not the definition of angle of incidence. Angle of incidence is the ray, the angle between the ray and the normal. In this case, 0, because they are along the same line. So if angle of incidence is 0, angle of reflection is going to be 0. So that's how you get option A. So be very careful about this definition. Okay, question 25. I got it wrong the first try. Okay, and the reason is because of the English being used here. It's quite confusing. So what I'm going to do is that I'm going to do you a favor of drawing it out. So this way is easier. Okay, so for the sake of going through, we are going to examine each of the option here. So let us start off with a grid. Okay. Okay, this grid is a very rough grid. On top here, we will have the undisturbed molecules. Below here, we will have the disturbed molecule. That means when the sound wave comes. So what happens is that we will have molecules that looks like this at the beginning. They are at their fixed position. Let's say they are stagnant. Then after that, when the sound wave comes, it's going to experience compression and all those things. So hard to draw also. So just one look, you can see that this one must be my compression. This one must be my refraction, then followed by compression, and then the refraction is on the other end. So let's establish this. Okay, you can see the top one is all the undisturbed air molecule. This is when the sound wave comes through. So you will have compression, refraction, compression, refraction. Okay, so the first statement A, here, molecules at the center of each refraction has 0 displacement. So if you look at center of refraction here, you can see that is aligned with the undisturbed one. So you know that A is correct. Okay, B, molecules of the wave move in the same direction as the wave propagates. So in this case, the wave is propagating in this direction. And you can see that this molecule has actually moved this direction. So you see the two direction is already in opposite way just by looking at one. Okay, and of course I'm not saying that it's always going to be opposite. If we look at this molecule versus this one, you see that it has actually moved this way. So yes, for some of the molecules it's going to move in the same direction as the wave propagation. Okay, but some of them are moving in the opposite direction. Even though it is parallel, it's opposite in direction. So we know that B is wrong. So we got our answer. But for the sake of going through this paper, we just examine each option. So option C, the molecules of the wave adjacent to those at the center of compression are at maximum displacement. So this is the center of compression, and the molecule adjacent to this is this one, and you can see that indeed, yes, this one has moved the most. You see this one almost 1/4 of it. This one just moved a little bit, okay, but this one has actually to move the most. Anyway, if you look at your graph, if I draw a displacement time graph, okay, it will look like what? So compression will be like so this is one wavelength, so down here is one wavelength. So you can see during the compression the displacement is 0, so displacement is 0. Okay, if I were to draw one wavelength, it will be like this. Yeah, so you can see that so you will have this here, this here. Is it a maximum displacement? This will be 1, 2, 3, 4. In fact, it is not. Okay, option C. That's weird. It is not really adjacent. If you look at this way. Okay, let me check about option C. Why is it this way? So I just note it down on my YouTube video. If you have a good explanation, do share with me. Maybe in the form of video or even in the form of a reply. Okay, why is C correct? Okay, because when I draw the distance displacement graph, it doesn't look right. Okay, anyway, let's move on to D. Distance between adjacent center of compression is equal to the wavelength of the wave. So this one makes sense because the distance between compression to compression is one wavelength. Yeah, so the distance between the molecules adjacent to the compression is also one wavelength. Even adjacent to this is also one wavelength, because you are moving molecules by one molecule length, one molecule unit. So as long as you keep that compression to compression, even you move adjacent to it or adjacent to it, is going to be one wavelength. Okay. Okay, 26. 26 is really very easy, this one. So ultraviolet and visible light. So ultraviolet just means that it has shorter wavelength, so you know that it's going to be A or C. Then because ultraviolet and visible light are in the same electron spectrum, it is going to be moving at speed of light, so it's going to be the same. We know that option C is your correct answer. Okay, question 27. Which of the following? So microwave, you know that it has to do with satellite TV, space, things like that. Submarine communication, don't do that. It uses what? Think about it. Okay. But it doesn't use microwave. Okay. Microwave is high energy, high frequency wave. When you're using it in submarine, okay, yes, you can use, but it is a waste of energy, because submarine, you want it to be efficient, so you do not want to waste unnecessary energy. Okay, so B is wrong. Okay, question 29. Question 29 is very interesting. I was stumbled by it. I do not know, like, I have been playing with my left hand. So down here anyway, once you see you have a magnetic field, there's a force altering the path of this unknown charge. Naturally, you start playing with your left hand, and no matter how you twist your left hand, you realize that you can't fit it into this context. And the reason why is because the force acting on this particle must be downwards, right? And the field is actually downwards. So you have your force and your field parallel to each other. So once you see this, you look at your left hand rule. The force and the field must be perpendicular, but in this case, the force and the field is parallel. So you know that it's not going to work. Your left hand rule is not going to work. So you know that your left hand is not going to work. That means this field cannot be a magnetic field. Yeah, it cannot be a magnetic field. Okay, if it is a magnetic field, the force won't be parallel to it. So you know that your B and D is wrong. So just examine A and C, see if it fits into the context of the question. So the option given to you is an electric field. So electric field, if this is an electrical charge, okay, there will be an interaction because like charge repel and unlike charge attract. So you can see that the charge is being attracted to the bottom. And if this is an electric field, it means that this one is your negative terminal, this is your positive terminal. Right? Because electric field line runs from positive terminal. So if the charge is moving away from the positive side, meaning that your charge must also be positive. So option C. Yeah? Okay. Okay, question 29. Question 29, they ask you in a different order, what will happen if you follow this procedure. So let's go through what will happen in each step. So when you bring the positive charge rod near to the cylinder, let's zoom it in now, what will happen is that you are going to induce negative charge here and positive charge here. Okay, but overall, the cylinder is still neutral because same number of electron and same number of negative charge and same number of positive charge. So I'm going through step by step. So that is what will happen when you bring it near. Number 2, you touch the cylinder with your finger. Once you touch the cylinder with your finger, what happens is that the electron from your finger is going to be attracted by the induced positive region in your metal cylinder, and because your metal cylinder is a metal, so meaning that the electron from your finger is going to flow and is going to pair up with the positive charge. Okay, so in a sense, now excess electron has gone into the magnetic metal cylinder, and so this no longer be neutral, it will become negative. Okay, no longer neutral. Then number 3, now you remove the rod. Now when you remove the rod, what will happen is that the electron here will no longer be induced to this side. It is going to be spread evenly into in the metal can. But because just now you have put in excess electron here, they will feel that, oh, there's a light charge here, it's going to repel. So what happens is that these negative charges is going to go through your finger and into the ground. So what happens is that this negatively charged metal can will now be neutral again. Then now you remove the finger. Well, what you will do is that nothing will happen, it will still be neutral. Okay, you just remove this part, that's all. So in the end, your cylinder will be neutral, uncharged. Okay, so A is your answer. Question 30 is quite simple. You need to use 2 formulas because you have to find the amount of charge flowing through the resistor, and you are told the time. So there's only one formula that will help you do that, is your I equals to Q over T. Your Q is the number of charge, I is the current, T is the time. The thing is that you do not know the current. It's not given directly in your question. But they tell you what is the potential difference, they tell you the resistance. So use your V equals to IR, find the I, change the I into Q over T, and then you can eventually find your Q. Yeah? Question 31 is about your resistance and resistivity. So concept you need to know is decrease in length would result in an increase in resistance. A decrease in area, sorry, the first one is wrong. First one is increase in length would increase the resistance. Decrease in area would increase the resistance. So you need, when you are looking at the resistance, you must consider both the length and the change in the length and the change in the area, cross-sectional area. So just examine all 4 of these, you will find that only C will give you twice the resistance, because length, no change, So constant A decrease by 2. So decrease by 2 means that increase by 2 times. So that's what you want, right? So C is your answer. Okay, question 32 is quite simple. Read the graph. You were told 30C. So from here, 30 degrees C, you find that this thing is 150 ohm. If you want to find the current in the circuit, apply the V equals to IR here. If you want to apply the V equals to IR here, you must first find the total resistance. So find the total resistance, apply V equals to IR in the circuit. So this is your total potential difference in the circuit. You will find the total current, your total resistance. So everything you are applying to the whole circuit. So that's why you use the total resistance, you find this. Then next, you know that this is in series, current is the same, so apply V equals to IR to this resistor only, because you want to find the potential difference across this resistor only, right? So your current is the same, the resistance is just this one, because you want to find the potential difference of just this one, so you get 3.6 volt. Finished. Okay.